Thank you very much for the introduction. And what a storm we had last night. Compared with the weather we had this summer, I think I wanted to give a touch to my presentation. I brought a little bit of summer in my slide, in the first slide especially, with a nice weather in the background. So my name is Claudio Nigro, as said, and I'm a PhD student working on a project for Malmö University and Chalmers, the boy. And I'm going to speak about some effect of hydrogen on metals, and especially in the areas such as aerospace and the nuclear power plants. So I would like to invite you to focus on this first picture. It was not only about the storm. So it's nothing uncommon here, except that it's a summerish picture. We have clouds, we have the blue of the sky, and in the middle, a shining and warming sun. But I'd like to focus on this warming sun here and get closer and closer. And if you have the chance to get out of space and have the right protection for the eyes, then you would probably see something like that. A giant ball of fire, burning and burning. It's gas. A gas. Yes, what gas? Hydrogen. Hydrogen is the most abundant component in the element in the universe. It is found in most stars, most planets, and in our solar system, especially in the gaseous planets. For example, Jupiter, where it composes for almost 90% of the planet. But what about our Earth, our blue planet? Some people, most people, think that hydrogen is seen as a gas, like in the leftover side picture. But actually, it can be found in many other substances, especially water. When we know that the Earth is covered by more than two-thirds of water, we can think that all our oceans, all the glacier, all the rivers are containing hydrogen. And also, we can find hydrogen in almost all organic matters. For example, oil. But not only oil. I would like to focus on this part that we actually, every people have in the body some molecules which is composed of hydrogen. Why? Because we are actually in majority made of water. Up to 60%, the human body is made of water, and hydrogen will be like that in every human being, every animals, every plants, every living things. So globally, our blue planet is a very big container and a very big source of hydrogen. And since its discovery in the end of the 18th century, hydrogen has been seen as this, a source of energy, just like a power cell. And through the years, scientists try to extract the energy from hydrogen. For example, I will show you some examples here. In the first picture on the left, upper side, we can see a system in order to extract the energy in form of power, electric power, using the same process that occurs in the sun, which is called fusion. Hydrogen can also be used as a fuel, for example, in our space area, in rockets, in order to propel the rockets and to put satellites in orbit, for example, or to send men in space. It can also be used as a fuel in the so-called the power cells, power cells in the cars, in the transportation area, so cars and trains. But who speaks about hydrogen to be used as energy? Speaks about how to store this hydrogen. How do we do that? So this last year, it has been a lot of development of a different way of containing this very corrosive and very small atoms of hydrogens. Yes, actually, in every material, or almost all of them, hydrogen is penetrates the material and can actually go into the material and probably provoke some damages. It can promote some failure. So hydrogen can be seen as a source of failure. I've shown here different examples of how hydrogen can provoke accidents. For instance, in the first picture on the left is an airship that is filled with hydrogen because of the difference of density with the air. It helps the airship to rise into the sky. But if there is any leak, anything, hydrogen is very reactive with oxygen. So when it encounters the oxygen of the air, can just explode. Just need a little trigger, and it can lead to such an incident, very catastrophic and dramatic. The same thing happens if you look at the second picture in the center. The same thing has happened in refineries. For example, here is the example of hydrogen contained in the walls of a tank which contained a very flammable gas. And the hydrogen that was contained in these walls helped cracks to propagate in the walls and to let the very flammable gas escape and provoke an explosion of the whole refinery. That was a very big incident in 1984 in the United States. In the last picture on the right is a pressure vessel which went into failure, as you can see. This was caused by it was found to be caused by the presence of hydrogen in weld, which promoted the propagation of a crack and which led to failure. Those are accidents that you don't want to see in sensitive areas such as the nuclear energy and aerospace. Of course, in the nuclear energy, you don't want to have an accident which would lead to a catastrophe when we speak about environment and human lives. Hydrogen in the nuclear power plant is found in form of water in the reactor. And of course, you don't want to have incident in aerospace. It's a lot of money at stake in aerospace. So if anything would happen with the fuel, so hydrogen, that would leak or explode, then it's a lot of million or billion dollars which are lost and wasted. And even human lives when it is the case. I would like to emphasize about how hydrogen, like here are some examples of how hydrogen can promote the failures of materials in these areas, but also generally. In the first picture up left, hydrogen is in the material and can help cracks propagating in the structure. It assists the cracks, as we would say. In the second picture, up right, hydrogen goes under it goes under the surface of the materials and form a ball of gas which can provoke the formation of blisters, I can see. As I said before, hydrogen can be found in welds, and that comes to the third picture, down left. And when it during the welding, hydrogen can become or recombine into gas and form little holes like that, which are also called fish eyes, which can be the initial site of for cracks, for cracking. I would like to focus on this last picture in the low part on the right, which is about the formation of new component in metals, especially in aerospace and nuclear areas. Those are special metals that react with hydrogen by forming new components, which are called hydrates. The metal can be titanium, zirconium, and there are others. And the alloys that they are associated with. This new component, called hydrate, can be seen as an analogy with rust. So here are some examples of rust. And as most people have seen rust in their life attacking iron, and could be the cause of failure or promote crack happening or the destruction of a structure. Yes, it is the same thing for hydrates. And in particular, I would like to emphasize the fact that hydrates are very brittle components, and that are much less tough with respect to fracture than the whole metal. And it can be promoted, the formation of hydrates can be promoted by the presence of stress in the metals. And I invite you to look at the last picture, where we are bolt. There we have induced stress by screwing this bolt in the structure, which leads to a concentration of hydrate all around these areas. I'd like now to speak a little bit about my research, because I'm working on the formation of hydrates, and what I'm doing is to model and to simulate the formation of hydrates in the presence of stresses. So here are some examples of what I'm doing. I'm using a computational model, and in order to look at the evolution of the formation of hydrates. For example, on the left is the first example of what I do. Like, I'm modeling the formation of hydrate in a metallic plate, which undergo a stress, which is applied vertically. And this stress, together with the presence of hydrogen, induces the formation of hydrate perpendicular to the direction of the applied load. In the second picture on the right, a crack is present in the plate. And as we open the crack, there is a concentration of stress in the neighborhood of the crack tip, which can also induce the formation of hydrates. And why do I do that? I do that. I make these models and simulations in order to, within the context of predicting failures of this kind of materials, hydrate forming materials, for aerospace and nuclear areas, and also to avoid making experiments which are usually expensive and onerous. I'd like to thank you for your attention. And if you have questions about this subject, I'm available to answer all of them.